Hello and welcome. Today we're going to talk about harmonic functions. Okay, so recall what a harmonic function is. We've seen these before in partial differential equations. A harmonic function is a function h, x comma y, which is, it takes an input that's in R2, over some domain in R2, and it spits out a real number. And it has the property then that h, the second derivative of h plus the second derivative in terms of y, the second derivative of h in terms of x and the second derivative of h with respect to y, those summed together are equal to 0. And of course, harmonic functions have a bunch of really important properties. That they're the steady state temperature on some domain D in the plane, or it could be an electrostatic potential, and so on and so forth. Okay, and we also know that it has a bunch of neat properties that if I take any path in the plane and I look at the gradient function of h and I dot it with an outward normal ds, it's equal to 0. And in fact, this defines the harmonic this equation here. And this is also called Laplace's equation. So harmonic functions are solutions to Laplace's equation, and it has this nice property where if I have any path that's sitting inside my domain, C, and then I were to look at the flux field defined by the gradient, and if I dot it with the normal, there's a dot product there, and those are normal vectors that are sticking out at 90 degrees. And if you take that, it's always going to be equal 0, and I always call that the 0 net flux property. And of course, this property, this 0 net flux property, also defines the Laplace's equation because we know the divergence theorem, which states that any flux like this is also equal to the integral over the area. In this case, I'll call it, well, I shouldn't call it D because we already called that. I'll call it C bar, which is basically, if C is the path around this region, C bar will be the entire area inside, and we'll say that that's equal to the divergence of this flux field over that area, where this is simply the divergence of our gradient field there, and this is precisely hxx plus hyy equals 0. And if that's true, if this is true for any C, any path in my domain, then that means that this is true. That means the integral itself, or the integrand inside of this integral, is equal to 0, which is precisely the expression of Laplace's equation. So 0 net flux, this expression of balance, the idea that the gradient field, this vector field, essentially, if I speak in kind of colloquially, it means that half the time the arrows of this vector field are pointing inward towards our area that's enclosed inside of C, and half the time it's pointing out. And it should balance so that the net flux is always 0. Okay, so those are the ideas behind what a harmonic function is in terms of kind of real-world modeling things. Steady state temperature distributions over some heat-conducting plate that's in 2 dimensions, or an electrostatic potential. Those are 2 examples. So the question then is, the question you might be having then is, how does this relate to functions of a complex variable, and specifically analytic f functions. Okay, because we just learned about this analytic business. So it turns out, and now let's go to visit a new page. That recall then that it turns out that if we write f of z is equal to u x comma y plus I v x comma y, that if f is analytic in some domain D of the complex plane, then u and v are both harmonic. That is, they solve Laplace's equation. So, why? How does this work? Well, we can, again, we go to the Cauchy-Riemann equations. Ux equals Vy, and Uy equals negative Vx. All right, so what I'm going to do then is I'm going to take the x derivative of this. That becomes Uxx. Provided these are smooth, okay? Again, the Cauchy-Riemann equations, provided these functions are continuously differentiable again, i.e. we can take a second derivative and it's continuous, then the Cauchy-Riemann, the satisfaction of the Cauchy-Riemann equations is equivalent to saying that f is analytic. So I can take this second derivative here, and that equals Vyx, okay? Now I take the y derivative, so that becomes Uyy equals negative Vxy. And because all these derivatives here are continuous, it means that this is also equal to negative Vyx, which of course is the same thing as the top row. Now if I add these two together, of course these two cancel and I get 0, and I get on this side Uxx plus Uyy is equal to 0. And I can leave it to you if you want to prove the same thing. Well, actually, let's just do it. Let's do it here. So now I'm going to do the same thing. Uxy is equal to Vyy. So now I'm taking this top row here, and I'm taking its y partial derivative instead of the x. All right, and the same thing here. If I go Uyx is equal to negative Vxx, I'm going to put that negative sign over there, just like that. And again, through that what we call the Clairaut's theorem in multivariate calculus, I can always exchange these derivatives. I can turn that into an xy mixed partial derivative. And again, I add them up, and I get 0 is equal to Vyy plus Vxx. So both u and v are solutions to Laplace's equation. Great. All right. So let's maybe go through some examples here of just what we can do here. Okay. So for instance, let's say I have the function f of z is equal to z squared. I know this is analytic because I know, and it's analytic entire. Recall our definition because it's true for every point in the whole complex plane. F prime of z is equal to 2z. Great. All right. So let's actually now let's see what we can find in terms of the u and v. So f of z is equal to z squared, which is equal to x plus I y squared, which is equal to x squared minus y squared. That's the real part, plus I 2xy. All right? So clearly right here, this is u of x comma y, and there is v of x comma y. All right. All right, so now we can check that these are both harmonic. Uxx is equal to 2 is equal to Uyy. I can just take those derivatives and sorry, nope, that's not right. That's equal to negative Uyy, right? And so when I add them together, I get 0. That's the solution to Laplace's equation. Similarly, Vxx is equal to 0, and Vyy is equal to 0. Of course, 0 plus 0 is also 0, and so this checks out. this is an analytic function, and that does seem to, we have the observation now for this particular example that the u and v are harmonic functions. The next thing to kind of assess here then is, this is a nice example here. So let's now go over another thing. So how do I make analytic fz functions? So if I just the question then is, if I just take two harmonic functions, I'll say, we'll call them, u and v, that satisfy Laplace's equation. If I just stick them together in a complex number like that, will it be analytic? And the answer is an emphatic no. If I just take two, I should really say arbitrary harmonic functions u and v, and this is because if I just were to take any two functions that are harmonic, and if I just compose them together in a complex number, they're not necessarily going to be they're not going to create an analytic function. It turns out that u and v are, to make an analytic function, u and v are, or I should say must be, matched. I.e., they must satisfy the Cauchy-Riemann equations. Again, always with the Cauchy-Riemann equations. So for instance, so let's just go back to another example. Let's go back to f of z is equal to z squared. That was equal to x squared minus y squared plus I 2xy. Well, v is equal to 2xy. That's a harmonic function. But so is, and I'll call this, v tilde 6xy, right? I just multiply by a constant number. Also harmonic. I've done nothing to it in terms of any kind of substantive change that should affect its harmonic properties. However, now if I pick g of z to be equal to x squared minus y squared plus I 6xy is not analytic. Okay, now, and that's pretty clear to see, and because we need u, if this is u and that's v, right? I'll call that v tilde now. Ux is equal to 2x, and vy is now going to be equal to 6x, which of course are not equal, like that. They're not equal, and so Cauchy-Riemann is violated. So G is not analytic. Okay, so what we see here is actually, so U and V are, so if I say if, so this is the conclusion here, if F is analytic, then U and V are especially matched. Okay, in fact, we actually have a name for it. U and V are called harmonic conjugates. They could also be called pairs, harmonic pairs. If that's that might be a more vague term, but the idea of a conjugate means they're especially paired functions, and that means essentially that they satisfy the Cauchy-Riemann equations. Okay, So let's go through an example. So let's say now I have some function. So suppose I have u of x comma y is equal to y to the third power minus 3x squared times y. So I can check real quick. Uxx, that's going to be equal to negative 6y. And then if I take u, y, y, you can see clearly that's going to be 6y. So of course you add those together and you get 0. Okay, and so clearly this is a harmonic function. So check there. But now I want to find, so I want to create an analytic function out of this, an analytic function out of the complex of a complex variable. I want to find v x y. That is conjugate to u. Okay, so that's pretty simple. We have to just use the Cauchy-Riemann equations. We know that ux is equal to vy. So we can compute what ux is here. So we see clearly that that's going to be equal to negative 6xy. All right. So now we have what v's y derivative looks like, and then we have u y is equal to negative, so I'm going to put the negative over there, is equal to vx, right? So let's find out what negative uy is. It's clearly going to be negative 3y squared minus 3x. The next thing I'm going to do then, of course, if I have both of these partial derivatives here, I can anti-differentiate. So now I'm going to anti-differentiate with respect to y here, and that's clearly going to be it's going to be negative 3xy squared. And then I have to, because I've done an anti-differentiation with respect to y, I get a plus c1 function of x. So again, if I were to take this derivative with respect to y, this thing would disappear. So I have to add that additive constant that could be a function of x. All right, so that's equal to now v. Okay, but now we're going to do the same thing here. We're going to take an antiderivative with respect to x. All right, and then we're going to get the same. So that's going to become then, we have to do this. So that's going to become negative 3y squared x. And we see that there's a correspondence between those two terms. Plus, and then I see something here that's going to be that's going to be, and then we have to take this antiderivative with respect to x here, so we get a 3/2 x squared. All right, so that's looking pretty good. I feel like I made a mistake here somewhere. See my mistake. I forgot there should have been an x squared there. Clearly, that definitely works. So, so what we had there was we had an x squared there, and now we're going to take its derivative again. So that becomes a plus x cubed. All right. So that looks good. And then again we add a plus c2, which now is a function of y. And then we look for correspondence. Clearly, this function that's purely of x, that could be x to the third. And this other mystery function of y that doesn't seem to show up anywhere else just has to be maybe a constant. So that just becomes plus c. So what we get is that v is equal to negative 3xy squared plus x to the third plus c. So we see right here, it's v is always going to be unique up to a constant. All right, so that's nice. So then again, my function f of z then is going to be equal to y to the third minus 3x squared y plus I x to the third minus 3xy squared. Okay, so there is my analytic function. All right. Of course, you're going to always add a constant to that, and it would also be an analytic function. But we'll just pick our constant to be 0. All right. Well, thank you very much.